Welcome to Opening Voices. I'm Quentin and I'm CEO of Clevercloud. We are still discussing with Philippe Notton, the CEO of SiPearl, the European company specialized in processor design. In this episode, we are talking about the evolution of CPU and semiconductor market. I'm still with Philippe Notton in Paris. We are speaking what is about a CPU. So last week we tried to describe what is a semiconductor market, what is a chip, and how we can manage to understand that. So going back to last week to that. So semiconductor market have been brought to life with the CPU, and there was a kind of status quo for, 10 to 15 years. And about 10 years ago, it tried to change. Maybe you can explain there what is the change and what's happening on the market like 10 years ago.
In fact, the first change probably happened in Europe. It was Jean-Claude Juncker, one of the president of Europe at this time, said that we need to limit dependencies. It was US technology, Intel, x86 were the dominant custom to push for something. At this time, ARM was still in Europe because it was a British company. It was before SoftBank and before the Brexit. They say, let's push a transition from x86 to ARM. And out of this, they initiated multiple initiatives to develop some, let's say, compute expertise in Europe up to ideally chip production.
So at this time, the smartphone era have already breaked up. So it was already a trending system
and given to ARM.
And all the smartphone, like huge majority of the smartphone was on ARM. I know that there was a few try on other architecture, but ARM was making the market. Maybe here we can describe what is the work of ARM. So it's a British company.
Or it was a British company.
It was a British company. And what is the work of ARM? What does it produce?
It's so-called an IP provider. An IP, intellectual property. It's an element of core technology you have to implement in your solution. You can make that, for instance, you're buying a house, you need to have the brick or the tiny elements. You're not going to buy the house as is. If you want to build yourself, you build the different components. And ARM is providing some tiny elements in terms of IP and especially the compute core, which is what we are using in our with our processor, on which you will put all the software.
So basically, ARM gives you part of design of a CPU, because the big work about the CPU is designing all the way you need to engrave the silicium to have all the logical, what we call logical gate, which is basically the way we design the tiny program of every instruction, isn't it?
Because from a core to a CPU, you have lots of stuff to add. First, in the CPU, you have multiple cores. In the CPUs, you have in your laptop or server, you can have 4 cores, 8 cores, 10 cores. In a CPU with the class, that the one we are building, we are talking about dozens of cores, because you want to have multiple VMs working at the same time in the CPU or to extend the computing power. Now, the way you need first to interconnect the core, because the core is computing some informations, but this information after has to be exhausted and transferred to other cores or to the external memory. So you need to have within the CPU some huge highways, or usually it's a mesh network to transfer these informations. And for this class of CPUs, we are talking about a bandwidth which will be higher than terabytes per second. So it's huge, the quantity of data. You can move from a core to another core, the core from a memory.
And we're speaking only to transfer the data inside the tiny chip, which is big like that.
Or from the chip to the memory, which is outside, like DDR5 or HBM, which can be in the...
But it is at this proximity of the CPU, just for the people...
Yes, that's very short-term range.
Because a lot of people think when we talk about terabytes about the network, but the problem of data transfer also happen inside the computer itself. And the magnitude of data transfer we are speaking about in the CPU or between the CPU and the memory is way bigger than the transfer happening in the network.
Yes, for multiple reasons. One of them is propagation, because when you want to transfer one information from this side to this side, and if you have 1 meter in between the 2 points, it's 3 nanoseconds to transfer. Now, when you do this within the chip or in between, let's say, a couple gates, you will talk about picoseconds, and that's the way you can say a fast compute. And this kind of propagation time, that's one of the limits today, everywhere. There are some theoretical limit. You cannot do what you want. And of course, it adds also lots of power management, because if you transfer too much information for the long distance, it uses much power. So the more compact it is, the better it is in terms of power efficiency. But also the drawback is that you concentrate lots of power in a small, let's say, in a couple square centimeters. So at the end, you need to exhaust this power to manage it and so there is no free lunch.
Okay, so that's something maybe people need to understand, that the level of velocity of the transfer and the number of the transfer inside the CPU is a very huge number, which is not the magnitude with the memory, not the magnitude with the hard drive or any storage system, and we don't speak about the network, which is absolutely totally different. It's the same kind of stuff, like going from your bedroom to the kitchen and from your bedroom to maybe Pluton, the far distant planet of the solar system.
That's correct, yes.
It's something very complicated to understand, but you need to be very, very quick at this.
Let's say it's at gate level. It's at almost at the atomic level. So it has to be very short distance if you want to compute this.
So ARM is not producing CPU yet. We can say maybe
not yet.
We will discuss the news a little bit later. So it's not producing CPU. It's only providing you some kind of IP and instruction, and it provided to many other companies around the world. Maybe we can discuss what are the companies producing some ARM CPUs in the world.
You have one quite famous, which is we're discussing smartphone at the beginning. It's not ARM, which is developing directly the chip for smartphone. For instance, it's Qualcomm, MediaTek. And them are ARM-based.
And it's a CPU you will find in many Android-based phones.
Yes,
this kind of
at the cost, which is, let's say, consumer level. So you will spend a couple $1,000 to have this CPU with 4-core or octa-core. Now they are used to say that you have Qualcomm, MediaTek, even Huawei in China. Even if this is, let's say, no longer in Europe, they are using ARM instruction set.
As they're producing their own.
As they develop their own silicon, they develop their own phone. That's the example of vertical integration. In the case of Apple, so they produce the phone, but they develop the chip also.
And so Apple is buying to ARM instruction set to produce their own CPU.
They are licensing the technology and the IPs. They are building their chip. Then they have the cost of the chip fully under control. So the chip margin is for them. That's let's say the 3 vertical integration. And what has this started maybe 10 years ago? Now the GAFAM, so the big, let's say, US clouder, Azure, Google, AWS, Meta, they have developed, or they're still developing their own chips.
Okay.
Why? Then they can have the chips really suitable for their own needs. And in terms of cost control, that's perfect. So instead of giving away a production margin to Intel, AMD, for NVIDIA, it's another topic, but for them, they can be very cost effective.
Right. So majority of companies producing chip today are using the ARM instruction set. So it's kind of very interesting that from smartphone, they jump progressively into other devices. So you say in the server, so in Amazon, you will have the Graviton, for example.
Yes, Graviton family, Cobalt with Azure. Yes, because at the end, it's an open system. So you need to be able to load multiple applications on, let's say, on top of the server. So you need an open instruction set, which is the case of what they do. But the main interest for them, I guess, before the instruction set is cost control. And the fact that the chip, the CPUs or TPUs or other accelerator we are building are fully customized for their own needs. Yeah. But they have the budget to manage it. So they can spend hundreds of millions of dollars to have their own chip for them, which is what the European clouder unfortunately cannot do because they don't have the volume, they don't have the scale to develop their own component.
And just to be clear with the listener, when we say there is an architecture and you use it, maybe it can hide another architecture. If you take, for example, an AMD x86 processor, the confidential computing instruction set which allow you to have like a secure enclave for cryptographic key or stuff like that is actually an ARM core inside x86.
Inside the big one, yes. And we can have multiple ARM cores inside of big CPU.
So it's really an instruction set and it will spread. Thus, there is another example. So you say that the majority of the phone are on ARM. So there is a huge coming on the server of the ARM. And thus there is another market where the ARM is really present?
Consumer
For the laptop, for example?
Qualcomm is starting, let's say, to ship CPUs for laptop. Yes, MediaTek will probably do it because Windows has been ported on ARM. It's cheaper. It uses less power. So yeah, for laptop, it's given. And what is a laptop today? It's just a big smartphone without the 5G internet.
And maybe another big producer. Maybe we can discuss about the M1 from Apple.
Homemade, yes. And if it works well.
And it's ARM too.
It's ARM too. It's just that they have developed their own core. They're using the same instruction set, so they did much more themselves on the.
So they're not buying so much IP from ARM than before. That's it.
In fact, they have licensed an access or the right to use the instruction set. And the rest below the instruction set, the core, they can develop it themselves. Now, they have a good team. They have the resources to do it. They have the money to do.
And that's why they are so efficient.
Because it's really targeted, tailored for their own needs.
That's very interesting. So what does SiPearl in this huge market? So you're focused on producing ARM CPU?
On designing, producing on the wrong.
Explain the difference maybe to this listener.
So in the semiconductor industry, you have two categories. You have the so-called integrated device maker. So they have their own fab. So they design and they produce their own chip. And we have the fabless.
So the design and produce their own chip, we can talk about Intel,
ST, for some verticals like sensors, power components. They are designing themselves, they're producing themselves, even in Europe and in France. Samsung. Yeah, Samsung is quite impressive also because they are no longer only, let's say, designing CPUs, baseband processor, and all the stuff for phone, but they have also the displays.
Yes,
they have the memories. And in a smartphone, you have plenty of memory. So it's really vertical integration at a huge scale. That's for the integrated one. Now it means that for this you need to have the volume, the budget and the volume, because managing a fab is quite complex. And you have the other category which are fabless. And in terms of fabless, you have AMD, you have Qualcomm, you have NVIDIA. So you can be number one and being fabless. You have plenty of other fabless companies. Is one of them.
Fabless is what? So you're just designing the chip?
Yes.
And after producing the chip itself, is made by other company.
So you design it, you own it. It's your own architecture, your own secrets, and you send it to a global fab, such as TSMC, such as Samsung, because their fab is open. Intel, they're also trying to open their fab.
But I see that Intel is struggling a little bit to open their fab.
Yes, because the strength of TSMC since day one is that in terms of logistics, in terms of the way they work, they can manage thousands of products in parallel, hundreds of customers. So their fab has been, let's say, designed for this.
But they never design any CPU. So
it's not their own product there, it's an open fab. So you pay, you have access to the foundry.
Okay.
So in our case, we're designing the product, and after to make it simple, we'll buy our product from TSMC.
But after the product is made by a supplier, TSMC, majority of the time it's TSMC. There is also
in compute in 90% of the case it's TSMC, yes.
And they send it back to you, and then you sell it.
We own it in all cases, and we sell it. Okay. The interest is that whatever is the volume we want, 100 PCs, 1,000 PCs, 1 million PCs, it's their problem. That we manage it. We don't have the issues of managing the fab, which is just impossible for what we are, let's say, doing, because the cost of such a fab, we are talking about 20 or 30 billion dollars. So just impossible. And
low barrier.
So low entry barrier, and that's part why there are plenty of, let's say, political discussions about having fabs in Europe. And a fab like TSMC works because they have multiple customers. It cannot work for one customer. And that's why also Intel is struggling today with its foundry, because they don't have enough Intel products to fill up Intel fabs.
And that's draw the accounting of Intel very low.
Because if a fab is not loaded at more than 80%, the fab is losing money.
Yes, because basically fab need to be operating 24 hours, 7 days per week, like all the time.
And fully loaded to be fine-tuned, because there is so-called a yield issue. So if you don't produce enough PCs out of your fab, the yield is going down. To fine-tune it, need to be very sharp in production, really.
So fab is about to be sure that your whole installation is fully loaded, because you cannot, it can work, it cannot be financially working, even for very high-end PCs, very expensive. If you just are not working for like 24 hours a day, but only 12 hours, the cost will not be twice, but will be like 4 or 5 times. Isn't it?
That's correct, yes.
So it's a very complex work to manage a fab. That's why it's not something you do.
No, and we cannot. We cannot. Let's say for financial reason, it will be useless. We won't be able to load it. It's a different business, and that's why, let's say, TSMC, is so strong.
And you can produce some SiPearl CPU at TSMC because NVIDIA is producing his own GPU.
No, NVIDIA is fabless also. So NVIDIA is producing also in TSMC. Yeah. But what's interesting and what we do is that Apple and NVIDIA AMD to use let's say, new processes. Like it was an announcement, a couple days ago about the new AMD CPU that is going to be in 2 nanometer in TSMC. That's very good, because there will be the first one. They debug the process, and once will be, let's say in our case, will be let's say a bit behind, but the process will be fully matured, thanks to AMD that, let's say, helped TSMC to.
Because to developing this new process will have cost like billions.
It's crazy, and of course, TSMC wants a provider with a good volume to debug it, to mature it, etc. So we'll just be, at least at the beginning, a bit behind, taking benefits of the algorithm.
So in this area, what does SiPearl? So you buy some instruction from ARM. You manage to create a CPU which has a good instruction set for the needs you see on the market. And then you produce with TSMC. And then you have a CPU which is designed in Europe, produced in Taiwan, but designed in Europe, which is reducing the level of dependencies we have to the USA, isn't it?
Yes, we can see it this way. So we license some elements, an IP from ARM to have the compute core. We have designed the other elements of the chip, let's say from architecture to final chip. It's and after, as you said, it's made in TSMC. The interest is that we know at 100% what is in the chip. We fully control the code. You can say it's kind of source code. In fact, it's at hardware level, but we control the source code. So we know perfectly. So there, in terms of risk of backdoor, etc., we know what's inside. It does not mean that it's bug free, but we know let's say we know the content. After it's going to production, a couple months after, we have the chip back. So it will go to a customer on their motherboards, which will be server or supercomputer, like Evident, which is developing the supercomputer for Jolish in Germany that we will discuss later on. Okay. But it's not only the fact that we control the content, it's also a question of creating value. Because the design team is in Europe, so mainly in France and Spain in our case. So this value is redistributed in Europe, because the engineers will be better and better, and this expertise remains in Europe.
And it's easy for us to make the SiPearl engineer. To be fair, I spent a lot of time with some the SiPearl engineer because we can discuss low-level optimization, very efficient for our usage, and that can be very financially interesting or environmentally interesting and stuff like that. So maybe about explain what is this. We will figure out next week what have been the roadmap and what have SiPearl does, and after we will discuss a little bit with Greg of the market of what exactly is the position of the market of SiPearl. So thank you very much for listening, and see you next week. Thank you for listening Opening Voices. We will continue our interview with the SiPearl team in a few days, so follow us and subscribe not to miss our next episode.